These two metal spheres, sitting just a few centimeters apart inside a sealed vacuum chamber, carry no electric charge, yet they are pulling on each other. That attraction is real, but faint enough that a thin film of static charge can easily mask it. A researcher walking down the hall, or a shift in building groundwater, can produce a larger physical disturbance than the gravitational pull of the spheres themselves. This is Newton's law of universal gravitation. In theory, calculating that force requires only a few inputs. You take the mass of the two objects, divide by the square of the distance between their centers, and multiply by a single universal number, the Newtonian gravitational constant, big G. We have to distinguish big G from lowercase g. Lowercase g describes the local acceleration produced by the Earth, a number that changes depending on your latitude, altitude, and the local geology. Big G dictates the overall strength of gravitational interaction between any two masses anywhere in the universe. Astronomers determine the product of big G and the mass of a planet with high precision by watching orbital motion. The orbit reveals the product of the two variables working together. Isolating G on its own, however, requires the mass to be independently and precisely known. That brings the measurement into the laboratory where manageable objects generate minuscule forces. Two 1-kilogram masses placed 10 centimeters apart pull on each other with a force of only about 6.7 billionths of a Newton. This measurement shifts the focus from the smooth paths of planets to the microscale disturbances inside a room. Finding G requires forcing a universal law into a tabletop environment. The first celebrated laboratory solution arrived over 2 centuries ago. Conceived by English scientist John Michell and used by Henry Cavendish in 1798, the experiment was designed to determine the density of the Earth, but it established the architecture for measuring big G. This diagram shows the core mechanism of a modern torsion balance. Large source masses move near smaller spheres suspended on a horizontal rod by a thin wire. As the large masses exert their pull, the suspended rod rotates, twisting the wire until the gravitational torque is balanced by the wire's resistance. In a simplified mathematical model, the restoring torque is proportional to the angle of rotation, like a perfect mathematical spring. Physical reality is less cooperative. A real fiber is not an ideal spring. It relaxes over time, its internal structure shifts, and it expands under small temperature fluctuations. A correction too small to matter in an ordinary instrument can shift a precision measurement of G. To account for these mechanical flaws, researchers use different techniques. Some measure how moving the source masses changes the natural oscillation period of the pendulum. Others use feedback loops to hold the pendulum near a fixed orientation, measuring the exact torque required to oppose the gravitational attraction. Using different methods is intended to expose hidden errors. In 2018, a team at Huazhong University of Science and Technology used 2 different torsion pendulum methods. Both reported very high precision, yet their final values were separated by about 300 parts per million.
When CoData evaluated the major measurements of G for its 2022 adjustment, the results were scattered beyond their reported uncertainties. Consequently, the committee multiplied those uncertainties by an expansion factor of 3.9 to acknowledge that the measurements disagreed more than they should. These conflicting results suggest that invisible physical effects are systematically interfering with the measurements. Precision alone does not guarantee that every systematic error has been found. Gravity has an inconvenient property that complicates any laboratory measurement. While electric fields can be blocked by conductive enclosures, as shown on the left, there is no known gravitational equivalent of a Faraday cage. Gravity passes straight through all barriers. Every surrounding mass continues to pull on the apparatus. Researchers must model the influence of seismic vibrations, changes in atmospheric pressure, the shifting mass of vehicles, or tides outside the building. The source masses themselves add complexity. Newton's equation is exact for point particles, but real spheres have a 3-dimensional density distribution. A tiny internal void or an uneven density gradient changes the gravitational field the mass produces. Because the force depends on the square of the distance, an error of just a few micrometers in the separation of the masses alters the result. The metrology of the objects becomes inseparable from the gravity measurement. Measuring a universal force requires the researcher to account for the physical state of the entire surrounding environment. This illustrates the challenge of systematic error. Random noise scatters data points, but they average out over time. A systematic error, however, repeats with the signal. It can produce tight, precise data that clusters around an incorrect value, making the wrong result appear increasingly reliable. For example, moving a heavy mass might subtly distort the floor or heat a support. This creates a secondary physical force that occurs whenever the mass moves, allowing it to mimic the gravitational signal. To find these errors, scientists invent unrelated techniques. Cold atom interferometers replace mechanical wires with freely falling atoms. Laser pulses place atoms into a quantum superposition, and the gravitational field changes their relative phase. This replaces a mechanical fiber with matter waves, introducing a completely different set of environmental challenges. A decade-long effort at the NIST Boulder laboratories used a torsion-balance approach with a concealed numerical offset to prevent human bias. Even with this procedural care, the result did not eliminate the broader disagreement among global measurements. While some suggest that G might fluctuate over time or location, the laboratory discrepancies do not yet establish a new physical effect. The current scientific consensus points to experimental systematics that are not yet fully understood. A physical constant is inferred through a model. We connect an observation, an angle, a period, or a phase shift to the constant G through the geometry and material properties of the instrument. The number remains difficult to pin down because every attempt to measure the attraction between two objects also measures the pull of the world around them.